The universe is a place of endless mystery, a grand cosmic stage where the laws of physics bend and twist in ways that leave even the brightest minds baffled. Out there, beyond the familiar glow of stars and planets, lie structures so strange, so utterly perplexing, that they seem to defy everything we think we know about space. Imagine staring into the night sky and realizing that some of those distant points of light aren't just stars, they're enigmas wrapped in layers of cosmic dust, celestial puzzles waiting to be solved. Today, we're setting off on a journey to uncover 25 of the most bizarre galactic structures ever discovered, each one a riddle scribbled across the fabric of the universe itself. From colossal rings of stars that shouldn't exist to galaxies shaped like cosmic question marks, these anomalies challenge our understanding of gravity, time, and even reality. Picture a whirlpool of matter spinning so fast it tears holes in space, or a cluster of galaxies arranged in a pattern so precise it looks like it was designed. These aren't just scientific curiosities, they're glimpses into the universe's deepest secrets, clues left behind in a cosmic detective story we're only beginning to piece together. And the most thrilling part, every answer we find only leads to more questions, pulling us deeper into the unknown. This isn't just a tour of strange sights, it's an invitation to wonder. What if these structures hold the key to understanding dark matter, or even the birth of the cosmos itself? What if they're evidence of forces we haven't yet discovered? As we explore these 25 galactic oddities, you'll see the universe in a whole new light, not as a static backdrop, but as a dynamic, ever-changing puzzle, one that's still being written. So buckle up, by the time we're done, the night sky will never look the same to you again. The first stop on our cosmic mystery tour takes us to a structure so vast it redefines the word enormous. Stretching an almost unimaginable 10 billion light-years across, the Hercules-Corona Borealis Great Wall isn't just big, it's a cosmic contradiction. When astronomers first spotted this behemoth in 2013, its very existence sent shockwaves through the scientific community. Picture a wall of galaxies so immense it would take light, the fastest thing in the universe, 10 billion years just to travel from one end to the other. That's longer than our planet has existed, longer than the sun has burned in our sky. What makes this structure truly baffling isn't just its size, it's how that size breaks one of astronomy's most fundamental rules. For decades, scientists operated under what's called the universal homogeneity assumption, the idea that when you zoom out far enough, the universe should look roughly the same everywhere. Matter should be evenly sprinkled like flour in a well-mixed batter, but the Hercules-Corona Borealis Great Wall shatters that expectation. Here, galaxies aren't scattered randomly, they cluster together in a pattern so dense, so deliberate, it's like finding a single, sprawling metropolis in what we thought was an endless, empty desert. So how did something this colossal stay hidden for so long? Part of the answer lies in its distance. This wall sits so far away we're essentially seeing it as it existed just a few billion years after the Big Bang. That makes it not just a structure but a fossil from the universe's youth. Some theorists suggest its formation might be tied to quirks in the early cosmos, where pockets of dark matter pulled galaxies together like cosmic gravity wells. Others wonder if we're seeing evidence of forces or phenomena we haven't even named yet. The discovery forces us to ask uncomfortable questions. Was our understanding of the universe's large-scale structure fundamentally flawed? Could there be even bigger formations lurking in the darkness between the stars? One thing's certain, the Hercules-Corona Borealis Great Wall isn't just a curiosity. It's a challenge, a cosmic riddle scrawled across 10 billion light-years of space, daring us to rethink everything we thought we knew. Just when we thought the Hercules-Corona Borealis Great Wall had stretched our understanding of cosmic scale to its limits, along comes a discovery that twists that scale into something even more bizarre, this time with perfect curvature. Meet the giant arc, a formation so vast it could connect Earth to the farthest edges of our observable universe more than 20 times over. This enormous crescent of galaxies stretches an astonishing 3.3 billion light-years across space, not in a chaotic tangle, but in a smooth, deliberate arc, like a smile etched across the cosmos. What makes this structure so unsettling to astronomers isn't just its size, it's the precision of its shape. According to everything we know about how the universe organizes itself, structures this massive simply shouldn't curve so elegantly. Picture throwing a handful of sand into the wind and watching it naturally arrange itself into a perfect spiral. That's the level of cosmic defiance we're dealing with here. When researchers first spotted the giant arc in 2021, they weren't even looking for it. They were studying distant quasars, the brilliant cores of ancient galaxies, when they noticed something odd. The light from these quasars revealed a pattern, a consistent trail of absorbed energy, tracing an arc across 9% of the visible universe. The real mystery lies in how such a finely curved structure could emerge at all. Current models of large-scale cosmic formations suggest that gravity, acting over billions of years, should create lumpy, uneven distributions of matter, like a broth slowly simmering into clumps, not a ribbon stretched taut across the void. Some theorists suggest the giant arc might be a fossilized echo from the universe's earliest moments, when mysterious pressure waves rippled through the newborn cosmos, leaving behind ghostly imprints. Others ponder whether we're seeing the influence of dark matter in ways we've never before detected, its invisible fingers sculpting galaxies into shapes that defy conventional physics. What's perhaps most humbling is that the giant arc isn't some distant abstraction, it's part of our cosmic backyard. At just 9 billion light-years away, it's close enough that its light carries secrets from a time when the universe was barely half its current age. Every new observation peels back another layer, revealing how little we truly understand about the forces that shaped and continue to shape the grand tapestry of the cosmos. One thing's clear, the universe has a flair for the dramatic, and it's not done surprising us yet. If the giant arc stretched our understanding of cosmic geometry, then the Sloan Great Wall and the CFA2 Great Wall tear apart the rulebook entirely. These aren't just collections of galaxies, they're sprawling metropolises of stars, gas, and dark matter, stretching 1.4 billion and 750 million light-years across space like frozen tidal waves of cosmic structure. The Sloan Great Wall, discovered in 2003, wasn't just a record breaker, it was a shock to the system. Imagine zooming out on the universe's map and finding a towering ridge of superclusters, each one a dense knot of thousands of galaxies, all threading together into a filament so vast it dwarfs anything in its cosmic neighborhood. What makes this wall so perplexing isn't just its size, but how its components align. Normally, galaxies distribute themselves like dandelion seeds scattered by the wind, but here they cling together in a spine-like formation, defying predictions about how dark matter should shepherd them apart over billions of years. Then there's the CFA2 Great Wall, a slightly smaller but no less mysterious counterpart. At 750 million light-years long, it's like a backroad compared to Sloan's superhighway, yet it poses the same fundamental question: how do these galactic traffic jams persist? Both walls act as cosmic freeways, with galaxies funneling along their lengths as if pulled by some unseen current. Current dark matter models suggest these highways shouldn't stay so coherent over such staggering distances. Gravitational forces ought to fragment them into clumps, dissolving their structure. The key might lie in something even stranger. Some researchers propose these walls are the fossilized imprint of sound waves rippling through the early universe, back when it was a seething, superheated soup. These waves, called Baryonian acoustic oscillations, could have left behind faint blueprints where matter clustered more densely, like tide marks on a shore. Others wonder if dark matter isn't behaving as we thought. its invisible scaffolding perhaps stickier or more structured than simulations predict. What's undeniable is that both walls force us to confront how little we grasp about the universe's largest skeletons. They aren't just curiosities, they're clues written in the language of galaxies, hinting that the cosmos might be far more interconnected, far more orderly in its chaos than we ever dared imagine. There's a galaxy so perfect it looks like it was crafted by cosmic hands, a golden core suspended inside a sapphire ring, floating in the void like a celestial jewel. This is Hoag's object, discovered in 1950 by astronomer Art Hoag, and 70 years later, it remains one of the universe's most photogenic and perplexing mysteries. At first glance, you might mistake it for a sci-fi artist's dream, a glowing yellow sphere of ancient stars encircled by a flawless blue ring of younger, hotter stars with a dark gap separating the two like a moat around a castle. But this isn't fiction, it's a real galaxy 600 million light-years away, defying every expectation of how galaxies should behave. What makes Hoag's object so baffling starts with that pristine symmetry. Most galaxies, even the elegant spirals, show some asymmetry: warped arms, lopsided bulges, or messy star formation. But here, the ring is perfectly balanced, as if drawn with a cosmic compass. The leading theory suggests a violent past, the collision hypothesis, where a smaller galaxy punched through the center of a larger one billions of years ago. The gravitational shockwave could have sent ripples through the galaxy's gas, compressing it into that stunning blue ring of newborn stars. Except there's a problem. No trace of the intruder galaxy remains, and the core of Hoag's object shows no signs of disturbance. It's like finding a shattered vase where the pieces somehow reassembled into a flawless sculpture, with no dust left on the floor. Even stranger, the ring isn't just pretty, it's practically a time capsule. The blue hue comes from massive young stars, suggesting active star formation, while the golden core houses older, cooler stars. Normally, galaxies don't segregate their stars so neatly by age. Some researchers propose that Hoag's object might be the result of a rare resonance, where gravitational forces align just right to herd gas and stars into separate zones. Others wonder if it's evidence of an entirely unknown galactic formation process, one that doesn't rely on collisions at all. The real kicker: Hoag's object isn't alone. Since its discovery, astronomers have spotted dozens of similar ring galaxies, but none as perfectly symmetrical. This raises even bigger questions. Is Hoag's object a cosmic fluke, or a sign that our universe holds more orderly secrets than we've dared to imagine? Every time we think we've cracked its code, the galaxy seems to wink back at us, its blue ring glowing with the quiet confidence of a puzzle that isn't ready to be solved. Rising from the heart of our Milky Way like two colossal smokestacks, the Fermi bubbles stretch 25,000 light-years into the darkness, one erupting above the galactic plane, the other plunging below. These twin towers of gamma-ray energy, discovered in 2010 by NASA, a Fermi gamma-ray space telescope, glow with the fury of a cosmic furnace, emitting radiation so intense it outshines the rest of the galaxy combined. Yet despite their staggering scale, each bubble large enough to swallow 15,000 Milky Ways stacked end to end, they remained invisible to us for centuries, hidden in plain sight until we learned to see the universe through gamma-ray eyes. What makes these bubbles truly bizarre isn't just their size, it's the way they defy explanation. Their energy signature doesn't match any known astrophysical process, flickering with patterns that leave physicists scratching their heads. Imagine finding twin volcanoes on Earth spewing lava at temperatures no natural process could produce. That's the level of mystery we're facing. The leading theory suggests they're relics of a cataclysmic feeding frenzy by Sagittarius, a star, the supermassive black hole at our galaxy's center. Roughly 3.5 million years ago, this sleeping giant may have awakened to devour a passing gas cloud or star, belching out jets of radiation and particles with enough force to punch through the galaxy's dense core. But here's the twist. The bubble's edges are razor-sharp, like they were carved by a cosmic knife, rather than fading gradually as explosions typically do. Some researchers propose this crisp boundary hints at an invisible magnetic field cocooning the bubbles, shaped by forces we don't yet understand. Others point to the bubble's strange cap structures regions of even more intense gamma rays at their tips as evidence of something far stranger at work, perhaps collisions between high-energy particles and the sparse gas floating between galaxies. The most tantalizing possibility, these bubbles might be our first glimpse of dark matter annihilations. If dark matter particles occasionally collide and destroy each other, as some theories predict, they could release the exact kind of gamma rays we see glowing from the bubble's hearts. It's a cosmic detective story where every clue leads deeper into the unknown, reminding us that even our home galaxy keeps secrets written in light we're only beginning to decipher. The Andromeda Galaxy seems familiar at first glance, our closest galactic neighbor, a swirling disk of stars we've studied for centuries. But peel back the visible layers and you'll find something far stranger, a hidden halo so vast it engulfs the entire local group, a sphere of superheated plasma stretching 2 million light-years into the void. That's right, while Andromeda's sparkling arms span a mere 200,000 light-years, this invisible shroud dwarfs it tenfold, a ghostly atmosphere so massive it could birth 50 more galaxies from its reservoir of gas alone. What's truly baffling isn't just the halo's size, it's the fact that it exists at all. According to our best models, gas this far from a galaxy's core should have drifted away eons ago, scattered by cosmic winds or stolen by intergalactic tides. Yet here it hangs, a gravitational defiance clinging to Andromeda like some kind of cosmic spiderweb. Scientists first caught whispers of this halo in 2020, when NASA's Hubble Space Telescope detected a faint ultraviolet glow around distant quasars, their light filtered through Andromeda's halo like a flashlight shining through fog. The data revealed a labyrinth of ionized gas, superheated to millions of degrees but somehow still tethered to the galaxy. The mystery deepens when you consider the halo's composition. Unlike the heavy elements forged in stars, this plasma is primordial, mostly hydrogen and helium left over from the Big Bang. It's as if Andromeda somehow preserved a piece of the early universe, a bubble of ancient chemistry untouched for billions of years. Some theorists suggest the halo might be fed by galactic fountains, where supernova explosions eject material outward, only for it to rain back down over cosmic timescales. Others propose it's the accumulated remains of cannibalized dwarf galaxies, their gas stretched thin across unthinkable distances. But here's the real head-scratcher: gravity alone shouldn't hold this structure together. At such extreme distances, the pull from Andromeda's core is weaker than a whisper too faint to prevent the gas from evaporating into intergalactic space. This has led to wilder hypotheses like hidden dark matter threads acting as cosmic Velcro, or magnetic fields we can't yet detect weaving an invisible cage around the plasma. Whatever the answer, Andromeda's halo is more than a curiosity. It's a challenge to our understanding of how galaxies live, breathe, and hold themselves together across the eons. One thing's clear: even the galaxies we think we know still guard astonishing secrets. Some corners of the universe feel almost too empty to be real, like someone took an eraser to the stars. The Boots Void is one such cosmic blank spot, a spherical desert of galaxies stretching 330 million light-years wide. If you stood at its center, you'd see nothing but darkness in every direction, no bright pinpricks of starlight, no hazy smudges of distant galaxies, just an overwhelming absence. Astronomers call these regions supervoids, but that term hardly captures their eerie significance. The Boots Void isn't merely empty. It's a hole in the cosmic fabric so vast it challenges our understanding of how matter distributes itself across the universe. Now imagine something even more unsettling: the Eridanus supervoid, a billion light-year stretch of near nothingness. That's a volume of space so large it could swallow 10,000 Milky Ways without a trace. What's startling isn't just the scale of these voids, it's how they contradict the universe's usual clutter. After the Big Bang, matter should have spread relatively evenly, like ink dispersing in water. Instead, we find these gaping voids flanked by dense walls of galaxies, as if the cosmos built sprawling cities separated by desolate wilderness. So how did these voids form? One leading theory points to quantum fluctuations in the early universe, tiny ripples in density that, over billions of years, became exaggerated. Areas with slightly less matter expanded into these cavernous voids, while denser regions collapsed into galaxies and clusters. It's like stretching a sheet of rubber. Thin spots grow thinner while thick spots bunch together. But some researchers argue these voids might be too large to explain this way. Their scale hints at something more exotic, perhaps relics of cosmic inflation, when the universe expanded faster than light itself, leaving behind pockets of unnatural emptiness. Then there's the wildcard theory, parallel universe collisions. Some cosmologists speculate these voids could be bruises from collisions with other bubble universes in the multiverse. Picture two soap bubbles bumping in a bathtub. Where they meet, space might stretch thin, creating voids in their wake. It's a controversial idea, but the sheer size of the Eridanus supervoid makes it hard to dismiss entirely. What's certain is that these voids are more than just empty space. They're cosmic pressure tests, forcing us to question whether our models of the universe's birth and growth are complete. After all, nothing reveals the shape of a room quite like the spaces between its walls. Galaxies aren't just drifting through space, they're racing toward something we can't see. Astronomers call this phenomenon the dark flow, and it's one of the most unsettling cosmic mysteries ever uncovered. Picture hundreds of galaxy clusters, each containing thousands of galaxies, all moving in perfect unison at speeds topping 600 kilometers per second, not scattered randomly, but streaming toward a single point beyond the edge of everything we've ever observed. It's as if the universe itself is tipping toward some unseen attractor, a gravitational anomaly so powerful it tugs on entire clusters like strings on a puppet, yet remains completely invisible to our telescopes. The first clues emerged in 2008 when scientists studying the cosmic microwave background, the afterglow of the Big Bang, noticed something odd. This primordial light, which has traveled nearly 14 billion years to reach us, showed subtle distortions, as if something massive were pulling on the fabric of spacetime from outside our observable universe. Normally, the CMB should look evenly distributed, like static on an old television. Instead, researchers found a strange tilt in the data, a pattern suggesting countless galaxies were caught in a cosmic current flowing toward something beyond our cosmic horizon. What could possibly exert such force? The leading theories range from the mind-bending to the downright apocalyptic. One possibility is a supermassive structure lurking in the unobservable universe, perhaps a colossal concentration of matter left over from the inflationary period, a relic so dense its gravity echoes across the void. Others suggest we're seeing the gravitational imprint of another universe entirely, a neighboring bubble in the multiverse brushing against our own. Then there's the more unsettling idea that the dark flow is evidence of a fundamental flaw in our understanding of gravity itself, a hint that Einstein's equations break down on scales larger than we've ever tested. Skeptics argue the data might be an illusion, a statistical fluke magnified by the sheer scale of the observations. But the dark flow's persistence across multiple studies makes that hard to swallow. Every new survey seems to confirm it, with galaxy clusters aligned in this eerie convergence like iron filings drawn to a magnet. If real, the implications are staggering. It would mean our universe isn't just expanding, it's being pulled, reshaped by forces from realms we may never see. The dark flow forces us to confront the limits of our cosmic vision. For all our telescopes and simulations, we might be like goldfish in a bowl, unaware of the hand that tilts the water. Whatever's out there beyond the curtain of the observable universe, it's rewriting the rules of the game, and we're only just beginning to glimpse its shadow. Deep in the cosmic darkness float glowing behemoths so strange they might as well be from another universe, Lyman alpha blobs, massive clouds of hydrogen gas that shine with ultraviolet light like celestial lanterns. These structures, some stretching hundreds of thousands of light years across, shouldn't exist according to our understanding of star formation. Yet there they glow, their eerie luminescence defying explanation, their energy output dwarfing what entire galaxies produce. The first of these blobs was discovered in 2000 by astronomers studying distant quasars, who noticed huge, diffuse halos of light where none should have been. What makes these blobs so puzzling isn't just their size, it's the source of their glow. Normally, hydrogen gas only emits this specific wavelength called Lyman alpha radiation when it's energized by newborn stars or active black holes. But in these blobs, the light is too uniform, too widespread to come from concentrated star-forming regions. It's like finding a city where every single streetlight shines with the brightness of a supernova, yet no power plant exists to explain it. Some blobs emit so much energy that if our Milky Way were placed inside one, it would look like a dim speck in comparison. One leading theory suggests these blobs might be cosmic lighthouses, illuminated by something far stranger, dark matter. According to simulations, the universe's dark matter forms an invisible web with filaments stretching between galaxies like scaffolding. Where these filaments intersect, they could compress ordinary hydrogen gas, heating it until it glows. If true, Lyman alpha blobs might be the first visible traces of this hidden cosmic architecture, marking the spots where dark matter's gravity sculpts the ordinary universe into radiant beacons. Another possibility is even more exotic. These blobs could be relics from the universe's infancy. During the first billion years after the Big Bang, vast reservoirs of hydrogen collapsed under their own gravity, forming what's known as cold flows. These rivers of gas funneled along dark matter filaments might have ignited into Lyman alpha blobs as they slammed together, their sheer kinetic energy converted into blazing ultraviolet light. If that's the case, we might be looking at cosmic fossils, snapshots of the universe's first attempts at building galaxies. Yet the biggest mystery remains their longevity. Many of these blobs have been shining steadily for billions of years, far longer than any known energy source could sustain them. Some researchers speculate that hidden black holes or never-before-seen particle interactions might be at work, while others wonder if we're witnessing an entirely new astrophysical phenomenon. Whatever the answer, Lyman alpha blobs remind us that the universe still holds dazzling mystery structures so vast and luminous they force us to rethink the very physics that lights up the cosmos. At the heart of the Phoenix cluster, 5.7 billion light-years away, a cosmic contradiction unfolds with such intensity it rewrites the rules of galactic survival. This monstrous galaxy cluster, one of the most massive structures in the known universe, hosts a core so violent and fertile it births stars at a rate 20 times faster than physics says it should, a phenomenon astronomers call the cooling flow paradox. Here, surrounded by an ocean of searing X-ray gas hot enough to vaporize entire solar systems, new stars ignite in a frenzy, defying every expectation of how galaxy clusters behave. The mystery begins with the intracluster medium, the superheated plasma that fills the space between galaxies in a cluster. In most clusters, as this gas cools, it should slowly sink toward the central galaxy, fueling gentle star formation. But the Phoenix cluster doesn't just cool, it hemorrhages star-forming material at a rate that would make our Milky Way look like a barren wasteland. Every year, this cosmic furnace churns out enough raw material to build nearly 740 stars the size of our Sun, a stellar assembly line running at impossible speeds. What makes this even more baffling is the role of the cluster's supermassive black hole. Typically, black holes act like cosmic brakes, pumping out jets of energy that reheat cooling gas and prevent runaway star formation. But in the Phoenix cluster, the black hole seems to be asleep at the wheel, its feedback mechanisms mysteriously muted. Without this regulatory pressure, the gas cools uncontrollably, collapsing into stars faster than any model predicted. It's like finding a forest where trees grow to full height in days instead of decades, a violation of natural rhythms on an astronomical scale. The implications ripple far beyond this single cluster. If such extreme cooling flows are possible, our understanding of galaxy evolution might be missing a critical piece. Some theorists suggest magnetic fields could be trapping cold gas near the core, creating pockets of star-forming fuel immune to reheating. Others propose that the Phoenix cluster represents a rare phase in cosmic history, a brief window when black hole feedback flickers out, allowing the universe to briefly revert to its wild star-forming youth. But the most tantalizing clue lies in the cluster's X-ray emissions. Maps from the Chandra Observatory reveal intricate spiderwebs of gas filaments, colder strands woven through the inferno, as if the intracluster medium is fragmenting into rivers of star fuel. This delicate structure shouldn't survive the violent environment, yet somehow it does, hinting at physics we've yet to account for, perhaps turbulence, perhaps unseen magnetic threads stabilizing the chaos. The Phoenix cluster doesn't just challenge our models, it forces us to confront how little we know about the life cycles of the universe's largest structures. In its fiery heart, stars are born against all odds, whispering that somewhere in the equations a variable is missing, one that might rewrite how we see the cosmos itself. The universe prefers curves, spiraling galaxies, round planets, the graceful arcs of orbiting stars. So when astronomers first spotted the Red Rectangle Nebula in 1973, its sharp angles and geometric perfection seemed almost alien. This bizarre structure, glowing crimson 2,300 light-years away in the constellation Monoceros, defies all expectations of how dying stars should behave. At its heart sits HD 44179, an aging binary star system slowly shedding its outer layers. Normally, such stars create spherical or spiral nebulae as they expire, not perfect X-shaped structures that look like cosmic blueprints. What makes the Red Rectangle so perplexing starts with its symmetry. The nebula's name comes from its appearance through early telescopes, a vivid red box with dark rungs that give it the look of a celestial ladder. But higher resolution images reveal something even stranger. Two cones of ejected material intersecting at precise angles, forming an X so crisp it could have been drawn with a ruler. Stranger still, these cones are hollow, their walls lined with evenly spaced knots of dust that create those distinctive rungs. It's as if the dying star didn't just exhale its outer layers, it somehow sculpted them into a geometric masterpiece. The leading theory involves HD 44179's binary nature. As the two stars orbit each other every 10 months, their gravitational tug-of-war could funnel ejected gas into two opposing jets, creating the cone shapes. But that doesn't fully explain the X's sharpness. Stellar winds and radiation pressure should blur those edges over time. Some researchers propose the answer lies in the system's thick dust disk. Normally, such disks spread material evenly, but here the disk might be warped, acting like a stencil that shapes outflowing gas into those crisp angles. Then there's the nebula's eerie color. The intense red comes from a rare form of luminescent carbon molecules called polycyclic aromatic hydrocarbons, which fluoresce under ultraviolet light. These molecules typically form in chaotic environments, yet in the Red Rectangle, they've aligned with the nebula's structure almost like pigment in a painter's careful strokes. Even more baffling, the same molecules have been detected in meteorites, hinting that dying stars like this one might seed the cosmos with the building blocks of life. The Red Rectangle challenges our assumptions about how chaos and order interact in space. Most cosmic structures emerge from turbulence, their forms softened by billions of years of gravitational interplay. Yet here, against all odds, geometry wins a fleeting moment of perfect symmetry carved into the void before the nebula dissipates into the darkness. It's a reminder that even in death, stars can create beauty so precise it borders on the impossible. At the heart of galaxy NGC 1277 lurks a gravitational monster so preposterously large it makes other supermassive black holes look like pebbles. This cosmic heavyweight doesn't just dominate its host galaxy, it completely upends our understanding of how black holes and galaxies grow together. While most central black holes account for a modest 0.1% of their galaxy's mass, this behemoth makes up a staggering 14%, tipping the scales at 17 billion times the mass of our Sun. It's as if someone replaced the steering wheel of a car with the wheel of an ocean liner. A mismatch so extreme it forces us to question whether we've misunderstood the rules of cosmic construction. The discovery, made in 2012, sent shockwaves through astrophysics. Black holes this massive shouldn't exist in galaxies as small as NGC 1277, a compact lenticular galaxy just a quarter the size of the Milky Way. According to prevailing theories, black holes and their host galaxies grow in lockstep, their masses proportionally linked through a delicate dance of mergers and accretion. The black hole's gravity influences star formation, while the galaxy's gas feeds the black hole, a symbiotic relationship that maintains balance across cosmic time. But NGC 1277's black hole breaks this harmony so spectacularly that some researchers wonder if we're seeing an entirely new class of object. One explanation suggests this black hole might be a relic from the universe's chaotic youth. In the early cosmos, dense regions of gas could have collapsed directly into massive black holes without first forming stars, a process called direct collapse. These primordial behemoths, born before galaxies fully took shape, might have grown faster than their surroundings, becoming gravitational anchors around which later galaxies formed. If true, NGC 1277 could be a rare time capsule, preserving one of these ancient monsters in a state the modern universe seldom replicates. But there's a catch. The galaxy itself shows no signs of the turbulence such a voracious black hole should create. Typically, oversized black holes blast their surroundings with powerful jets, heating gas and quenching star formation. Yet NGC 1277 is quietly middle-aged, its stars orderly and calm. This tranquility raises even thornier questions. Could the black hole be somehow inactive despite its size, or are we missing a crucial piece of black hole physics that allows such giants to exist without disrupting their homes? Perhaps most intriguing is the possibility that this black hole didn't grow gradually at all. Some simulations suggest it might be the product of a freak galactic collision, where multiple black holes merged in rapid succession without the usual feedback mechanisms kicking in. Picture a snowball rolling downhill, gathering mass unchecked while the landscape around it remains strangely undisturbed. If this scenario holds, NGC 1277's black hole might not rewrite the rules so much as highlight how wildly the universe can behave when standard processes get thrown out the window. Whatever the explanation, one thing is clear: this gravitational anomaly forces us to rethink the textbook story of galaxy evolution. It stands as a cosmic paradox, a black hole so massive it shouldn't exist, in a galaxy so calm it shouldn't host it, challenging us to either revise our theories or accept that the universe has more tricks up its sleeve than we ever imagined. Racing toward our galaxy at nearly 300 kilometers per second, the Smith Cloud is a cosmic bullet nobody saw coming, an 11,000 light-year long river of hydrogen gas on a collision course with the Milky Way. Discovered in 1963 by astronomy student Gail Smith, this enormous structure arcs high above our galactic plane like a tidal wave frozen mid-crash, its leading edge already beginning to splinter as it meets the halo of hot gas surrounding our galaxy. But the real shock came decades later when telescopes revealed this isn't just another gas cloud, it's a cosmic orphan carrying chemical fingerprints that shouldn't exist in our galactic neighborhood. What makes the Smith cloud extraordinary starts with its composition. When astronomers analyzed its light using the Hubble Space Telescope, they found sulfur and heavy elements at levels nearly matching those in our Sun, far richer than expected for a simple intergalactic wanderer. These elements, forged in stellar furnaces, suggest this cloud spent time inside a galaxy before being violently ejected. Yet despite decades of searching, no visible galaxy remnant accompanies it, no trail of stars hints at its origin. It's as if someone fired a cannonball made of galactic shrapnel into deep space, leaving only the glowing gas as evidence. The leading theories about its birthplace read like pages from a cosmic detective novel. Some propose it's the shredded remains of a dwarf galaxy torn apart by the Milky Way's gravity eons ago, a victim of galactic cannibalism whose stars scattered while its gas condensed into this high-velocity stream. Others suggest it might be fuel from the Magellanic Clouds, our galaxy's satellite neighbors, ripped away during a close pass and set on a billion-year journey back toward us. Then there's the wildcard idea that the Smith cloud is a dark galaxy fragment, a pocket of primordial gas that never quite managed to form stars before being captured by our galaxy's pull. The most tantalizing clue lies in the cloud's trajectory. Detailed radio observations show it's not just falling toward us, it's piercing through the Milky Way's disk at a steep angle, a maneuver that would require unimaginable energy. Simulations suggest this path is only possible if the cloud was launched by something cataclysmic, like a close encounter with a massive object we can't yet see. When it finally collides with our galaxy's spiral arms in about 30 million years, the impact will trigger fireworks of star formation, seeding new stellar nurseries with its rogue chemistry. Perhaps the most humbling realization is that the Smith cloud might not be unique. Recent surveys hint at dozens of similar gas streams threading through our galactic halo, each potentially carrying its own story of extragalactic exile. They remind us that galaxies aren't static islands, they're dynamic ecosystems, constantly exchanging matter with the void, forever reshaped by invisible tides we're only beginning to map. The Smith cloud isn't just a curiosity, it's a messenger from the intergalactic wilderness, proving that even the emptiest corners of the cosmos still have tales to tell. In the cosmic sea of bright spirals and blazing starburst galaxies, Dragonfly 44 drifts like a ghost, a wisp of visible stars stretched across a volume as large as the Milky Way, yet glowing with just 1% of our galaxy's light. Discovered in 2016 by the Dragonfly Telephoto Array, a telescope designed to spot ultra-faint objects, this galaxy shouldn't exist according to conventional astrophysics. Its stars are so sparse you could fly a spaceship through it for thousands of light years without seeing a single sun, yet its gravity tells a different story, one written almost entirely in dark matter. What makes Dragonfly 44 so unsettling is the sheer scale of its invisibility. Measurements of its star motions reveal a mass comparable to the Milky Way's, meaning this faint smudge of light weighs as much as our entire glittering galactic home. But here's the kicker, 99.99% of that mass is missing no stars, no gas, just an unfathomable halo of dark matter holding everything together like an unseen hand. It's as if someone took a normal galaxy and erased 99 out of every 100 stars, leaving behind a skeleton of gravity with barely any visible flesh. The discovery sent shockwaves through astronomy because it exposes a glaring gap in our understanding of galaxy formation. Current models suggest dark matter halos should collect ordinary matter gas and dust, which then condenses into stars. Yet Dragonfly 44's dark matter somehow failed to gather enough visible material, creating a cosmic paradox, a heavyweight in mass, a featherweight in light. Some theorists propose it might be a failed galaxy, a structure where star formation was mysteriously stifled, perhaps by intense early bursts of supernova explosions that blew away its gas. Others wonder if we're seeing a galaxy that formed in an unusually quiet pocket of the universe, where sparse intergalactic matter left it starving for star fuel. Even stranger, Dragonfly 44 isn't alone. Dozens of similar ultra-diffuse galaxies have been spotted in the Coma cluster, each defying the expectation that big mass must mean bright stars. This raises profound questions. Could the universe be teeming with these dark galaxies, lurking undetected because they're nearly transparent? If so, our census of cosmic structures might be missing an entire population, like mapping a city by counting only its streetlights while ignoring the buildings. The implications ripple beyond astronomy textbooks. If dark matter dominates galaxies like this so completely, it might mean our current recipes for galaxy formation need rewriting. Perhaps dark matter isn't just scaffolding for visible matter, but can sometimes build entire structures on its own, invisible empires where gravity reigns without the glow of stars. Dragonfly 44 doesn't just challenge our models. It whispers that the universe's greatest structures might be the ones we can't even see. Hidden behind the thick band of stars and dust that makes up our Milky Way's disk, something colossal is pulling. Thousands of galaxies, including our own, are streaming toward a gravitational anomaly so powerful it bends the fabric of spacetime itself, dragging everything in its wake at speeds exceeding 2 million kilometers per hour. Astronomers call this cosmic puppet master the Great Attractor, and its location in the direction of the Centaurus constellation makes it one of the most tantalizing and frustrating mysteries in modern cosmology. The problem: this gravitational behemoth lies directly behind the zone of avoidance, a region so clogged with dust and stars from our galaxy's bulge that traditional telescopes can barely peer through. Initial observations in the 1970s and 80s revealed galaxies behaving oddly, their motions suggesting an unseen mass roughly 250 million light-years away was yanking them off course. But the Great Attractor isn't just pulling a few stray galaxies, it's orchestrating the motion of entire superclusters, including our local group, in what scientists term the dark flow. The scale of this influence immediately posed a baffling question. What could possibly wield that much gravity without being visible? One leading theory points to the Norma cluster, a dense knot of galaxies sitting near the suspected epicenter of the Great Attractor's pull. Packed with bright ellipticals and swirling spirals, this cluster is massive enough to explain some but not all of the observed gravitational effects. Imagine tossing a pebble into a pond and watching the ripples spread. Norma's gravity might create local disturbances, but the Great Attractor's reach implies something far grander at play. Enter the Shapley supercluster, a sprawling metropolis of galaxies 500 million light-years beyond the Great Attractor. Some researchers argue this gargantuan structure, the most massive concentration of matter in our cosmic neighborhood, could be the true source of the pull. Picture standing at the base of a mountain so vast its slope pulls you forward even before you see the peak. That's the Shapley supercluster's proposed effect. Yet even this doesn't fully account for the motion of galaxies closer to us, leaving a glaring gap in the math. The most tantalizing possibility: the Great Attractor might not be a single thing at all, but the combined gravity of an entire network of dark matter filaments, invisible threads weaving through the cosmos, connecting clusters and superclusters in a vast, unseen web. Simulations suggest these filaments could funnel galaxies along specific paths, creating the illusion of a central attractor when we're really seeing the aftermath of spacetime itself being stretched and warped by hidden structures. But here's where the mystery deepens. Recent X-ray and infrared surveys piercing the zone of avoidance have revealed hints of previously unknown galaxy clusters lurking in the Great Attractor's shadow. These findings raise the electrifying prospect that we might be standing on the shore of a cosmic ocean, only now glimpsing the tides. Whether the Great Attractor is a known structure magnified by unseen mass, a new class of gravitational anomaly, or simply a waypoint on our galaxy's billion-year journey toward something even larger, one thing is certain: the universe still holds cards it hasn't shown us. And every clue we uncover only pulls us deeper into the dark. Some cosmic collisions leave scars, tangled wreckage of spiral arms, or lopsided plumes of scattered stars. But every now and then, the universe delivers a bullseye. The Cartwheel Galaxy, a dazzling ring structure 496 million light-years away, looks less like the aftermath of a galactic crash and more like a target painted across the void. Its perfect concentric circles of blue star-forming regions ripple outward from the core like waves from a stone dropped in a pond, except this stone was another galaxy, slamming through the center at 500,000 kilometers per hour. What makes the Cartwheel so mesmerizing isn't just its beauty, it's the precision of its physics. When astronomers first spotted this rare ring galaxy in 1941, they assumed such symmetry would be simple to explain. After all, we know how shockwaves work: toss a pebble into water and the ripples spread evenly. But simulating the Cartwheel's formation has proven maddeningly elusive. The problem isn't the collision itself, it's the timing. For interstellar gas to compress into those flawless rings instead of chaotic clumps, the impact had to occur at an exact moment in the galaxy's rotation cycle, like striking a gong at the precise millisecond its vibrations align. Here's where the mystery deepens. The smaller intruder galaxy, likely a spiral like our Milky Way, didn't just hit the Cartwheel's center dead-on. It passed through at a 30-degree angle, a glancing blow that should have skewed the rings into ovals. Yet somehow, the resulting shockwaves corrected themselves, spreading outward with near-perfect circular symmetry. Current simulations can't replicate this self-healing geometry without tweaking variables beyond observed cosmic conditions. It's as if the galaxy's gas acted like a liquid with memory, snapping back into perfect rings against all expectations. The secret might lie in the Cartwheel's unique anatomy. Unlike most galaxies where gas is clumped unevenly, this one's interstellar medium appears unusually uniform, a smooth reservoir that could allow shockwaves to propagate cleanly. Then there's the dark matter factor. Some theorists suggest the galaxy's invisible halo might be shaped like a sphere rather than a flattened disk, creating a gravitational buffer that stabilized the expanding waves. Others propose the intruder galaxy was moving at a very specific speed, fast enough to punch through without sticking around to distort the rings, but slow enough not to shred the target galaxy entirely. Yet the biggest clue might be the Cartwheel's vibrant blue outer ring, where newborn stars blaze in a perfect circle. This ring marks the leading edge of the shockwave, where compressed gas collapsed into stellar nurseries. Normally, such star-forming regions would be scattered randomly, but here they trace a line so exact it could have been drawn with compasses. This precision suggests the shockwave didn't just spread, it amplified, like a tsunami growing as it reaches shallower water. The implications stretch far beyond this one galaxy. If we can crack how such perfect rings emerge, it might rewrite how we understand galaxy collisions altogether. Not as chaotic crashes, but as cosmic orchestrations where timing, angle, and physics align to create fleeting masterpieces. The Cartwheel Galaxy doesn't just challenge our models, it offers a glimpse into a universe where chaos and order dance on a razor's edge. For all its violent origins, this celestial bullseye stands as proof that even in the darkest depths of space, perfection can emerge, if only for a cosmic instant. Hovering above the Milky Way like a ghostly crown, the Virgo overdensity is a sprawling cloud of stars stretching 5,000 light-years across, an enigmatic structure that shouldn't exist in our galaxy's quiet suburbs. Unlike the orderly spiral arms or the dense central bulge, this celestial oddity is a haphazard splash of stars adrift in the galactic halo, untethered from the Milky Way's familiar architecture. Discovered in 2006 during the Sloan Digital Sky Survey, this starry anomaly has sparked a cosmic detective story with two competing plotlines. Is it the mangled corpse of a devoured dwarf galaxy or a ripple in the Milky Way's very fabric? The dwarf galaxy theory paints a violent picture. Billions of years ago, a small satellite galaxy, perhaps 1/10 the Milky Way's mass, may have strayed too close to our galaxy's gravitational grip. Tidal forces would have stretched and shredded it, scattering stars like cosmic breadcrumbs across the halo. Supporting this idea, the overdensity stars move in concert, their velocities hinting at a shared origin. Chemical analyzers add weight to the case. Many stars here are metal poor, typical of ancient dwarf galaxies that formed before heavy elements flooded the universe. Yet there's a hitch. The overdensity lacks a clear core or dark matter halo, the usual fingerprints of a cannibalized galaxy. It's like finding a splatter of paint without the can, evidence of a mess but no clear source. Enter the warping hypothesis. Our Milky Way isn't the flat, stable disk it appears to be. Its outer edges undulate like a tablecloth ruffled by invisible hands, a dynamic flexing caused by gravitational interactions with nearby galaxies and dark matter clumps. Some astronomers argue the Virgo overdensity could be a stellar knot in this warp, a congregation of stars tugged out of alignment by these cosmic tides. Simulations show the Magellanic Clouds, our galaxy's largest satellites, might be the culprits, their gravity disturbing the Milky Way's outer disk enough to fling stars into this strange configuration. If true, the overdensity isn't an invader. It's a homegrown anomaly, a testament to our galaxy's fluid dance with its surroundings. But here's the twist: the overdensity stars aren't just warped, they're weirdly diverse. Some are ancient relics, while others are surprisingly young, suggesting multiple origins. This has led to a hybrid theory that we're seeing both a disrupted dwarf galaxy and warped Milky Way stars superimposed, like two ghostly images overlapping in a photograph. Recent Gaia spacecraft data adds fuel to the fire, revealing substructures within the overdensity that could be the mangled remains of multiple dwarf galaxies, all chewed up and spit out by our galaxy's gravity over eons. The Virgo overdensity forces us to confront how galaxies evolve, not as isolated islands, but as dynamic ecosystems shaped by collisions, tides, and invisible forces. Whether it's a galactic fossil or a ripple in the cosmic pond, one thing's clear: even our own backyard holds mysteries that defy simple explanations. As telescopes peer deeper, this stellar puzzle might just reveal how fragile and resilient a galaxy's identity truly is. Drifting through the cosmic deep like a celestial tadpole frozen mid-swim, this peculiar galaxy isn't just another spiral or elliptical, it's a cosmic accident caught in spectacular slow motion. The Tadpole Galaxy, officially known as UGC 10214, sports a tail so long it would stretch from our Milky Way to Andromeda with room to spare, a 280,000 light-year filament of stars, gas and mystery that rewrites the rules of galactic destruction. Most galaxies with tails are victims of gravitational harassment, their stars yanked away by passing neighbors, leaving behind faint stellar streams. But the tadpole's tail isn't just debris. It's a stellar nursery glowing brighter than entire dwarf galaxies, with newborn stars igniting along its length at rates that leave astronomers stunned. Here's the puzzle: tidal tails should be graveyards, not cradles. When galaxies interact, the violent gravitational forces typically shred star-forming gas clouds, not nurture them. Yet Hubble Space Telescope observations reveal clusters of massive young stars burning blue-hot along the tail's spine, some so fresh they're still wrapped in their birth cocoons of cosmic dust. The anomalies don't stop there. Spectroscopy reveals a strange chemical gradient along the tail's length. Regions near the galaxy's body are rich in heavier elements like oxygen and neon, while the outermost tendrils show compositions nearly as pristine as the early universe. This shouldn't happen. Tidal forces ought to mix everything together like a cosmic blender, not sort elements with such precision. It's as if some unseen hand carefully arranged the debris field by atomic weight, a phenomenon that challenges our understanding of how turbulence and chemistry interact in galactic collisions. One radical theory suggests the tail isn't purely tidal at all. The intruder galaxy, likely a compact spiral, may have punched through the tadpole's disk at a very specific angle and speed, creating shock waves that didn't just strip material away, but compressed it into perfect star-forming pockets. Computer simulations show these collision parameters could explain some of the tail's structure, but they fail to replicate the chemical sorting. That's led some researchers to propose an even wilder idea, that the tail is actually threading along a pre-existing dark matter filament, its invisible gravity shepherding gas into lanes of differing density and composition. Then there's the timing problem. The tadpole's tail is too long, too well preserved for a typical collision. Most galactic tails dissipate within a few 100 million years as their stars scatter into the void. Yet this one stretches nearly a quarter of the way across our local galactic neighborhood, its structure improbably intact despite what should be eons of cosmic weathering. Some astronomers speculate we're catching it at a unique moment, like stumbling upon a shattered wineglass mid-splash, frozen in some impossible stasis where physics bends to preserve the artistry of destruction. What makes the tadpole galaxy truly extraordinary isn't just its bizarre anatomy, it's the way this single object forces us to rewrite multiple chapters of astrophysics textbooks. From star formation triggers to elemental sorting in chaos, from dark matter's invisible influence to the timescales of cosmic collisions, every observation peels back another layer of assumptions. This isn't just a pretty Hubble portrait. It's a masterclass in celestial mechanics, proving that even the universe's most violent moments can produce structures of unexpected precision and beauty. The Bullet Cluster presents us with a cosmic car crash of unimaginable scale. A high-speed collision where two galaxy clusters plowed through each other at nearly 50 million kilometers per hour, leaving behind a scene that forever changed our understanding of the universe's invisible architecture. What makes this 1.7 billion light-year distant wreckage so revolutionary isn't the glowing plasma or scattered galaxies, but where those components aren't. When astronomers first mapped this system in 2006 using NASA Chandra X-ray Observatory and gravitational lensing techniques, they expected to find mass aligned with visible matter. Instead, they uncovered something astonishing. The bulk of the cluster's gravity wasn't where the stars and gas were. The Bullet Cluster had literally ripped the universe's veil, showing dark matter and ordinary matter living separate lives for the first time. Here's how the cosmic dissection works. When these two clusters collided, their diffuse clouds of superheated gas, the most massive visible component, slammed together like two ghosts walking through a wall, creating a shockwave of X-ray emitting plasma that now glows between the clusters. But the galaxies themselves, along with something invisible, behaved differently. Stars are so widely spaced that they passed by each other unaffected, like two swarms of bees flying through one another. Meanwhile, the dark matter, which outweighs ordinary matter here 5-to-1, also slipped through the collision unscathed, revealed only by how its gravity bent light from background galaxies. The result, three distinct fingerprints: X-ray hot gas stalled in the middle, galaxies sailing onward, and dark matter's gravitational signature even farther ahead, completely divorced from the visible wreckage. This separation is the smoking gun for dark matter's existence. If gravity worked as Einstein described without invisible mass, the lensing effect would follow the plasma, the majority of ordinary matter. That it doesn't prove something massive and unseen is calling the shots. Yet the Bullet Cluster's legacy isn't just confirmation, it's complication. The way dark matter coasted through this collision suggests it interacts even more weakly than we thought, not just ignoring light, but barely noticing itself. Most theories predicted some self-interaction, a slight drag as dark matter particles brushed past each other. Instead, they behaved like phantom ships in the night, passing without a whisper. The implications ripple across cosmology. If dark matter really is this aloof, it challenges models of how galaxies formed in the early universe. Simulations relying on self-interacting dark matter to explain certain galactic structures suddenly face tough questions. Some researchers propose an even wilder idea that the bullet cluster might contain multiple flavors of dark matter, with some particles interacting while others don't. Others wonder if we're seeing hints of dark matter's quantum nature, where wave-like properties allow it to spread smoothly through collisions, but the real shocker. The bullet cluster isn't unique. Similar offset collisions have since been found, like the musket ball cluster and Abell 520, each showing varying degrees of matter divorce. Yet none are as pristine as the original. Some show dark matter lagging rather than leading, or gas that's been stirred by subsequent encounters. This suggests dark matter's behavior might depend on energies we're still mapping, like cosmic-scale particle physics waiting to be decoded. What began as proof of the invisible now teases us with deeper mysteries, not just that dark matter exists, but how it dances when no one's watching. As the ultimate natural particle detector, the bullet cluster does more than confirm theories, it forces them to evolve. Every new observation peels back another layer, revealing a universe where the rules we've written might just be footnotes in a much stranger story. And out there, in the darkness between collisions, untold experiments of scale and violence are unfolding, each one holding secrets about the fabric we're only beginning to grasp. If the Fermi bubbles in our Milky Way are like twin smokestacks belching gamma rays, then Andromeda's version looks more like a cosmic jellyfish, a sprawling, lopsided structure with tendrils of high-energy radiation curling through its halo. Discovered in 2017 by the Fermi Gamma Ray Space Telescope, these bubbles stretch at least 4,000 light-years from Andromeda's core, glowing with the same telltale gamma-ray signature as our own galactic outburst. But the similarities end there. Where the Milky Way's bubbles are symmetrical and sharply defined, Andromeda's are ragged and asymmetrical, with one lobe stretching nearly twice as far as its counterpart. This isn't just a cosmetic difference, it's a cosmic clue that the rules governing galactic core eruptions might be far messier than we thought. The mystery starts with scale. Our Fermi bubbles tower over Andromeda's, spanning 25,000 light-years compared to its neighbor's more modest structure. At first glance, this makes sense. The Milky Way's supermassive black hole, Sagittarius A star, is about twice as massive as Andromeda's. But if black hole size alone dictated bubble size, we'd expect proportionality, not this wild discrepancy. Even stranger, Andromeda's bubbles show stark energy variations along their length, with gamma-ray intensity flickering like a faulty neon sign. Our bubbles, by contrast, glow with eerie uniformity, their radiation levels dropping smoothly from core to edges. It's as if two chefs used the same recipe but produced entirely different dishes, one precise and layered, the other haphazard and uneven. What could explain such divergent architectures? One leading theory points to Andromeda's turbulent past. Unlike the Milky Way's relatively quiet history, Andromeda has cannibalized multiple dwarf galaxies, each merger stirring its central black hole like a spoon in a cup of coffee. These disturbances might have triggered repeated, weaker outbursts, creating overlapping bubbles that merged into today's lopsided structure. Supporting this, computer simulations show that multiple small eruptions can produce the patchy, asymmetrical gamma-ray glow we observe. Meanwhile, the Milky Way's symmetrical bubbles suggest a single, catastrophic event. A black hole feast so violent it belched out energy in one coordinated burst. Yet the plot thickens when we examine the bubble's surroundings. Andromeda's gamma-ray structures align suspiciously with its vast, invisible halo of hot gas, that same primordial plasma we discussed earlier. Some astrophysicists speculate this halo might act like a cosmic sponge, absorbing and reshaping the bubble's energy. In the Milky Way, where the galactic halo is thinner and cooler, outbursts could punch through cleanly, creating those crisp boundaries. This would mean a galaxy's atmosphere plays as big a role as its black hole in shaping these eruptions, adding a new variable to an already complex equation. Perhaps most puzzling is the timing. Andromeda's bubbles appear younger than ours, just a few million years old compared to the Milky Way's 3.5 million-year-old structures. If both galaxies' black holes erupt on similar schedules, why aren't their bubbles in sync? Some researchers suggest dark matter might be the hidden variable. If Andromeda's central black hole orbits within a particularly dense knot of dark matter, its gravitational tugs could delay or distort outbursts. Others propose that magnetic fields stronger in Andromeda's core might channel energy unevenly, explaining those twisted tendrils of gamma rays. The takeaway is both humbling and thrilling. These twin sets of bubbles, so similar in composition, so different in form, are like cosmic control experiments, revealing how much we still don't understand about galactic hearts. They prove that supermassive black holes don't play by a universal rulebook. Their tantrums are shaped by everything from merger histories to galactic weather. And with each new observation, we're reminded that even our nearest galactic neighbor operates on logic we're only beginning to decipher. A reminder that the universe reserves its most fascinating lessons for those who know where to look. The dark flow isn't just a mystery, it's a cosmic trail of breadcrumbs leading to something far stranger than we ever imagined. Recent observations have added a chilling twist to this enigma. The direction of this galaxy cluster migration aligns unsettlingly well with one of the universe's most baffling features, the cosmic microwave background cold spot. This frigid patch in the afterglow of the Big Bang, a region spanning nearly 2 billion light-years where temperatures dip mysteriously low, shouldn't exist according to standard cosmology. Yet there it sits like a shadow on the cosmic microwave sky, and now we find galaxy clusters streaming toward it as if drawn by some unseen hand. The connection between these two phenomena has sent theorists spiraling into uncharted territory. One radical explanation suggests we're seeing the gravitational imprint of a pre-Big Bang structure, a relic from a previous universe or a neighboring bubble in the multiverse. Picture our universe as a soap bubble forming on the surface of a larger, unseen cosmic ocean. The gravitational tug of another nearby bubble could create distortions in our own, leaving behind anomalies like the cold spot and giving galaxy clusters a subtle nudge in that direction. It's an idea that borders on science fiction, yet the math holds surprising weight. Simulations of colliding universe bubbles show they could produce both temperature dips in the CMB and large-scale flows of matter, exactly what we're observing. But the plot thickens when we consider alternative physics. Some researchers propose the dark flow might be evidence of a fundamental asymmetry in the universe's expansion, a leftover lopsidedness from the moment of creation. Imagine blowing up a balloon unevenly, with one side stretching faster than the other. Matter caught in this uneven expansion would naturally drift toward the slower expanding region, creating the illusion of a gravitational pull. If true, the cold spot could be a fossilized echo of this primordial imbalance, a scar from when spacetime itself was born slightly crooked. Then there's the dark matter wildcard. Could these flows be tracing the contours of an unseen superstructure, a vast network of dark matter filaments weaving through the cosmic web? The cold spot scale matches predictions for where such filaments might intersect, creating gravitational wells deep enough to steer entire clusters. Yet even this explanation runs into problems, as no known form of dark matter should cluster on such massive scales without leaving other detectable signatures in the CMB. The most unsettling possibility: we're witnessing the limits of our physics. The dark flow and the cold spot might be the first cracks in our understanding of gravity itself, hinting that Einstein's equations break down over distances larger than we've ever tested. It's as if we've been studying ocean waves our whole lives, only to suddenly notice the tide pulling everything toward an unseen horizon. Whether the answer lies in other universes, forgotten asymmetries, or entirely new physics, one thing is certain: the dark flow isn't just pulling galaxy clusters. It's pulling our gaze toward the edge of known cosmology, where the map runs out and the real adventure begins. Rising from Saturn's north pole like a cosmic honeycomb etched into the atmosphere, the hexagon is one of the solar system's most mesmerizing mysteries, a 30,000-kilometer-wide storm with razor-sharp edges, whirling in a near-perfect six-sided pattern that defies every expectation of planetary weather. Discovered by Voyager in the 1980s and later studied in stunning detail by Cassini, this atmospheric behemoth isn't just a curiosity. It's a laboratory for physics so extreme, it might hold clues to forces shaping structures a million times larger, from galaxy clusters to the cosmic web itself. What makes Saturn's hexagon so baffling starts with its geometry. Planetary storms, even the most violent, tend toward spirals or ovals. Think Jupiter's Great Red Spot or Earth's hurricanes. Yet here, against all odds, a stable hexagon has churned for at least 4 decades, possibly centuries, its 6 sides maintaining military precision as winds scream at 320 kilometers per hour. The secret might lie in an invisible dance between fluid dynamics and planetary rotation. Laboratory experiments with spinning fluids have recreated crude hexagons, suggesting the shape emerges when turbulence and rotation reach a precise balance, like cream swirling in coffee, just right to form temporary patterns. But Saturn's version is no fleeting ripple, it's a monument to stability, a structure so durable it outlasts every human civilization that's ever tried to explain it. Here's where the cosmic connection sparks. The same physics governing the hexagon's formation, shear forces, differential rotation, and standing waves, might operate on scales so vast they boggle the mind. Across the universe, galaxy clusters swim in oceans of superheated plasma, threaded by magnetic fields and shaped by forces strikingly similar to those in Saturn's atmosphere. Computer simulations show that under certain conditions, plasma in these clusters can self-organize into hexagonal-like cells, vast cosmic foams where galaxies gather along invisible boundaries. The hexagon, in essence, might be a miniature model of processes shaping the largest structures in existence, a planetary scale hint at how order emerges from chaos across the cosmos. Even more tantalizing is the hexagon's eerie resemblance to another phenomenon: quark-gluon plasma patterns theorized to exist microseconds after the Big Bang. When physicists smash particles at nearly light speed in colliders, they briefly recreate this primordial soup, and some models suggest it, too, can form hexagonal arrangements under extreme conditions. If true, Saturn's storm becomes more than weather. It's a bridge between the infinitesimally small and the astronomically large, a demonstration that the universe might favor certain patterns no matter the scale. Yet the hexagon guards its secret stubbornly. Why 6 sides, not 5 or 7? Why does the structure remain locked to Saturn's rotation rate when the winds inside rage independently? And most perplexing, why is there nothing like it at the South Pole? These unanswered questions ripple far beyond planetary science. They remind us that sometimes the keys to galactic mysteries aren't found in the depths of space, but spinning right next door, a 6-sided whisper that the universe's grandest designs might be written in geometries we're only beginning to recognize. Among the countless quirks of the cosmos, few are as quietly unsettling as the discovery that supermassive black holes separated by billions of light-years appear to be spinning in sync. Picture 2 tops spinning on opposite sides of a planet, their axes inexplicably aligned despite never having touched. Now scale that up to quasars, the universe's most luminous objects, powered by black holes so massive they warp spacetime itself. When astronomers analyzed the rotation axes of nearly 100 quasars scattered across the sky, they found something that defies chance. These cosmic powerhouses weren't oriented randomly. Instead, their spins showed eerie coordination, as if threaded together by invisible cosmic strings. This alignment, dubbed the quasar polarization anomaly, first surfaced in 2014 when researchers noticed a strange pattern in the polarized light emitted by these distant monsters. Normally, each quasar's axis should point in a random direction, following the cosmological principle, the bedrock assumption that the universe looks roughly the same in every direction when viewed on large enough scales. Yet the data revealed a spine-tingling trend. Quasars in certain regions shared alignments spanning billions of light-years. We're not talking about a handful of oddballs. Entire swaths of the cosmos seem to be nodding in agreement, their black holes spinning in concert like dancers following some unseen choreography. Theories to explain this cosmic synchrony range from the provocative to the downright revolutionary. One camp suggests these alignments might trace back to the universe's infancy, when space-time itself stretched during inflation, the explosive expansion that occurred a fraction of a second after the Big Bang. If space-time carried primordial, wrinkles, or defects cosmic strings left over from this epoch, they could have imprinted preferred directions on the matter that later collapsed into quasars. Think of it like stretching a sheet of rubber with faint grooves. Everything forming atop it would naturally align with those hidden tracks. But here's the twist. Such structures shouldn't persist across the observable universe without violating the cosmological principle. Unless, and this is where things get wild, the universe isn't as uniform as we thought. Some theorists speculate we might be seeing the fingerprint of a pre-inflationary structure, a relic from before the Big Bang that somehow survived inflation's smoothing effect. Others propose even more radical ideas, like the influence of a multiverse, where neighboring universes exert subtle gravitational tugs that nudge black holes into alignment. Then there's the dark matter angle. If dark matter isn't perfectly uniform, if it flows in vast rivers or sheets, its gravitational pull could steer the growth of supermassive black holes over cosmic time. Simulations show that dark matter's invisible scaffolding might guide galaxy spins along preferred axes, like trees bending in a persistent wind. Yet even this explanation struggles to account for the sheer scale of the observed alignments. The implications are staggering. If confirmed, these coordinated spins could force us to rewrite cosmology's foundational assumptions. The cosmological principle isn't just academic, it's the cornerstone of how we interpret the universe's expansion, its age, and even its fate. A universe with preferred directions would be fundamentally stranger than the one we thought we knew. For now, the quasar alignment remains a tantalizing maybe. Some researchers argue the signal could be an artifact of observational bias or incomplete data. But as telescopes probe deeper and map more quasars, the pattern persists, whispering that we might be glimpsing the first threads of a cosmic web far more intricate and far more mysterious than we ever imagined. From perfect hexagons stamped across planetary storms to quasars spinning in eerie unison, the universe whispers a tantalizing secret. It adores patterns we don't yet understand. These aren't isolated oddities, they're pieces of a grander puzzle, one that suggests our cosmic rulebook might be missing entire chapters. Take geometry, for instance. Saturn's polar hexagon mirrors the cell-like structures seen in galaxy cluster plasma, while the Red Rectangle Nebula's sharp angles echo the precise rings of the Cartwheel galaxy. On scales vast and tiny, from quark-gluon soups to superclusters, nature seems to revisit the same blueprints, as if some fundamental law of organization transcends size and substance. Then there are the alignments, those spine-tingling moments when the cosmos winks at us with choreography that defies randomness. Quasars spinning in sync, galaxy clusters drifting toward unseen attractors, even the dark flows haunting correlation with the CMB cold spot, all hint at a universe more interconnected than our models predict. It's as if invisible threads stitch the cosmos together, nudging matter into formations that shouldn't persist across billions of light years. The kicker. These patterns often emerge where chaos should reign. Galactic collisions should scramble stars into disorder, yet the tadpole galaxy's tail sorts elements like a cosmic librarian. Black hole eruptions should be messy, yet the Milky Way's Fermi bubbles glow with eerie symmetry. Energy anomalies thicken the plot. Lyman alpha blobs shine without visible power sources. The Phoenix cluster births stars at impossible rates, and dark matter, whatever it is, holds galaxies together without interacting with light. These aren't just gaps in knowledge, they're glaring contradictions. Standard cosmology relies on uniformity and predictability, yet here we see structures that behave like they're following a different set of rules entirely. The Hercules-Corona Borealis Great Wall shouldn't exist if matter is evenly distributed. The giant arc's graceful curve shouldn't hold its shape across 3 billion light-years. Yet they do. What binds these mysteries? A growing suspicion that we're seeing the fingerprints of deeper physics, perhaps dark matter's hidden influence, relics from before the Big Bang, or even echoes of a multiverse. Each anomaly is a crack in the foundation of our understanding, inviting us to consider that the universe might be far stranger, far more ingeniously structured than we ever dared dream. The most thrilling realization: we're not just cataloging curiosities, we're decoding the universe's sly way of teaching us how much we've yet to learn. The mysteries we've explored aren't destined to remain mysteries forever. A new generation of astronomical instruments is rising, each designed to peel back cosmic secrets with unprecedented precision. Leading this charge is the Vera Rubin Observatory, perched high in Chile's Atacama Desert, poised to unleash the most ambitious sky survey in history. Unlike traditional telescopes that study one patch of sky at a time, Rubin's 8.4-meter mirror and 3.2 gigapixel camera will capture the entire visible southern sky every few nights for 10 years, creating a time-lapse movie of the universe on an unimaginable scale. This relentless gaze will catch fleeting phenomena: exploding stars, wandering black holes, interstellar visitors, but its true power lies in mapping the invisible. By tracking subtle distortions in billions of galaxies, Rubin will trace dark matter's hidden web with more clarity than ever, potentially revealing if structures like the Hercules-Corona Borealis Great Wall are cosmic accidents or signs of deeper physics at work. While Rubin scans the heavens, the Laser Interferometer Space Antenna LISA will listen to the universe's hidden symphony. Slated for launch in the 2030s, this trio of spacecraft will form a gravitational wave detector spanning 2.5 million kilometers, sensitive to ripples in spacetime from mergers between supermassive black holes. These collisions might hold the key to anomalies like NGC 1277's impossibly massive black hole. If LISA detects merging black holes of similar scale, it could mean such behemoths form differently than we thought, perhaps through chains of collisions in dense galactic cores or even exotic dark matter interactions. But the most revolutionary insights might come from missions targeting specific cosmic oddities. The European Space Agency's Athena X-ray Observatory, launching in 2035, will dissect the Phoenix cluster's runaway star formation with spectroscopic precision, hunting for the magnetic and turbulent forces that allow cold gas to survive its infernal core. Meanwhile, NASA's proposed Lynx telescope could peer into the hearts of Lyman alpha blobs, using ultraviolet vision to map their structure and energy sources like never before. Even farther ahead, concepts like the Cosmic Microwave Background Stage 4 experiment aim to scrutinize the CMB cold spot and its possible link to the dark flow, searching for patterns that could confirm or append our ideas about the universe's infancy. The coming decades will also see a revolution in computational cosmology. Next-generation supercomputers running advanced simulations will recreate these puzzling structures in digital universes, testing whether they emerge naturally from known physics or demand radical revisions. Projects like the Dark Energy Spectroscopic Instrument are already creating three-dimensional maps of millions of galaxies, letting scientists compare the real cosmic web structure to theoretical predictions with unprecedented statistical power. If discrepancies persist, if the giant arc and similar formations remain statistical impossibilities, we may need to embrace concepts like primordial magnetic fields, modified gravity, or even echoes of a pre-Big Bang universe. What ties these efforts together is a recognition that cosmic anomalies aren't just curiosities, they're pressure points where our understanding might crack open to reveal deeper truths. Each new instrument serves as both microscope and time machine, probing scales and epochs previously beyond our reach. As these tools come online, they won't just answer existing questions, they'll unveil phenomena we can't yet imagine, ensuring that the universe's capacity to astonish remains as infinite as its mysteries. The golden age of cosmic exploration isn't behind us, it's just beginning. From colossal galactic walls that shouldn't exist to perfect hexagons spinning on distant worlds, these 25 cosmic oddities aren't just scientific curiosities, they're proof that the universe thrives on the unexpected. Every time we think we've mapped the limits of space, it tosses another puzzle our way, bending the rules we thought were written in stone. The beauty of these enigmas isn't just in their strangeness, but in what they reveal about our own journey of discovery. They remind us that the cosmos isn't a static museum exhibit. It's a dynamic, evolving masterpiece, still painting itself in strokes we're only beginning to recognize. Consider how much we've learned and how much remains hidden. A century ago, we didn't even know other galaxies existed beyond the Milky Way. Now, we're grappling with black holes spinning in sync across billions of light years and dark matter weaving invisible scaffolds between galaxies. These structures aren't just outliers, they're signposts pointing toward gaps in our understanding, urging us to dig deeper. The giant arc's graceful curve, the phoenix cluster's defiant star factories, the eerie alignment of quasars, each one whispers that there's more to the story than gravity, dark matter, and the laws we've scribbled in textbooks. What's truly exhilarating is that this list of 25 is just the beginning. For every mystery we've uncovered, there are countless others lurking in the shadows of our telescopes, waiting for the next leap in technology or the next curious mind to piece them together. The universe doesn't reveal its secrets easily, but that's what makes the hunt so thrilling. Every anomalous structure, every impossible formation is an invitation to question, to theorize, and to marvel at how much we still don't know. So here's the real takeaway: stay curious. Whether it's the ghostly glow of the Virgo overdensity or the violent ballet of the bullet cluster, these cosmic riddles belong to all of us. They're not just puzzles for astronomers, they're reminders that wonder is woven into the fabric of reality itself. Now it's your turn. Which of these 25 structures captivates you the most? Drop your pick in the comments and let's keep the conversation as boundless as the cosmos we're exploring. After all, the next great discovery might start with a simple question: what if we've been missing something extraordinary?